to Spirit of Maths, the channel devoted to mathematical curiosities. In today's video, we will tackle the isoperimetric inequality, or how among all the shape of same perimeter, the circle gives the largest area. This fascinating question has been around since ancient Greece. Among all closed curves with a given perimeter, which one encloses the largest area? And in this video, what is fascinating about this question is that I can convince you easily and intuitively of the result, but we will see that the proof of the rigorous proof of the result needs some sophisticated mathematical tools. So what is the problem? If you take a rope of length L and you start making closed curves with this rope, you get for any such curve an area enclosed in this curve. And you can see easily that depending on the form you give to this closed curve, the area can become larger or smaller. And it's easy also to see that there is an ideal situation when your curve is a circle and you can see that in this way we get the largest area. So now in this situation we can give a relation between the area and the length of the curve L. We have that the perimeter L is equal to pi r, where r is the radius of the circle, and the area is pi r power 2. And of course we have this relation L square is equal 4 pi a3. So since intuitively we have seen that all other situation we get, all other curve we get, the area must be less than a3. So we get what is known as the isoperimetric inequality. L square is equal bigger than 4 pi the area. And now in this video I will show rigorously this inequality, and as we will see, this needs some mathematics. So we have now the isoperimetric inequality. So we take a curve of length L, and we will prove that L square is bigger than 4 pi the area enclosed in the curve. And it is what is known as the isoperimetric inequality. To do so, to give the proof, we will also prove that we have the equality that L square equal to 4 pi a, if and only if the curve is a circle. So it's a strong result, and we will go through it. Now, how we will deal with this problem? First, we need to make some analysis we have a geometric situation here, so we start by giving a parameterization of C, the curve C. This means that we give a function from R to C. We identify the plane as C such that fr is equal to C. Of course, f must be periodic of period L. And we will compute the perimeter and E in function of f, as we have down in the case of the circle. And the core of the proof is the use of Fourier analysis to establish Wirtinger inequality. Wirtinger inequality is one inequality famous in analysis. So we need to recall some results about Fourier analysis. And finally, we establish the isoperimetric inequality. So if you stick around until the end, you will know Wirtinger inequality and how Fourier analysis can be used to establish this result. So let's start. So we have our situation. We have a curve of length L, and we are concerned about the area inside this curve. So first we give a parameterization of the curve C. It's a map from R to C of class C1, and it's L periodic. So and we suppose that it is injective in the restriction of the interval 0L to get that the curve is simple. There is no crossing in the curve. And we can suppose also that we cross our curve with a constant speed, namely we suppose that we have this situation. Such thing exists always, and we can, from any parameterization of the curve, we can build one which satisfies this relation. And now we have this relation. So if you compute the length of L is the integrand from 0 to L, the module of the derivative of S, and you get, since the module is equal to 1, you get that L. And now we will compute the area. And the area is the double integral over the interior of C of du dv. We will write this in this form by taking this quantity equal to 1. And why we do so? We do so to apply Green-Riemann formula. So Green-Riemann formula give us that this integral is equal to the curvilinear integral over C of this one form. And now if we replace P by 0 and Q by U, we get here this formula. U S d de V is equal to V prime S. So we have now the formula which gives us the area within C in function of the parameterization. Now we will recall some basic facts about Fourier analysis. And Fourier analysis deals with the t-periodic function integrable on an interval on R, because they are periodic, and the Fourier to any such function we associate its Fourier coefficient given by this formula. So ANF is 2 over t, the integral of fx cosine n omega x, and BNF is equal to the integral fx sine n omega x, where omega is 2 pi over t. And for 0 we have A0f equal to the 1 over t, the integral of f is this, and we have always B0f equal to 0. So we associate to any t-periodic function these two sequences, and we associate the Fourier series given by this formula. Now the main result of this theory tell us that actually in many cases this Fourier series converge to the original function f. And we have the Dirichlet's theorem, which says that if f is piecewise continuously derivable on 0t, then the series Fouriers converge to the average of the left limit and the right limit of f at x, where f, so we have if f is continuous at x, this series converge to f. And the second important result of this theory is the Parseval identity, which give a relation between the L2 norm of f with the L2 norm of its Fourier coefficients. So we have this formula, the integral of 1 over t of the L2 norm of f is equal to this the sum of this series. Okay, so now we have the two main results we need in order to prove Wirtinger inequality. Now let's go to Wirtinger inequality. For Wirtinger inequality, we have a t-periodic function which is continuous and piecewise C1, such that its integral is equal to 0 on the interval 0t. So we have this inequality. The integral of g square is less or equal to t square over 4 pi square, the integral of its the integral of the square of its derivative. When t is equal to 2 pi, here we get 1, and we get that. And moreover, there is an important part. We have the equality if and only if our function is a combination of cosine and sine. So we have, this is Wirtinger inequality. No, now let's give the proof. The proof of Wirtinger inequality is based on Fourier analysis. So let's start. We know from the Parseval identity that this integral is equal to this one, because A0G is equal to 0 by hypothesis, and we have this the same for the derivative of t, and we have also A0, the derivative of g, equal to 0 because g is periodic of period t. This integral is equal to 0. Now we have there is relations between Fourier coefficient of g and Fourier coefficient of its derivative. And we start by a n g prime 2 over t, this integral, and now by integration by parts, we get that is equal to this quantity. Now this quantity vanish because g is periodic, and cosine 2 pi over t and t is also periodic of period t. So between 0 and t, this quantity vanish, and we are left with this relation. Now we recognize here the b n coefficient of g, and we have this relation that a n g prime is equal to 2 pi n over t b n g. We can get the same result when we start by bn here. The only thing we will change, we will get a minus sign. So we have now these two relations. We have this one, and we have these two relations between Fourier coefficients of g and Fourier coefficients of g prime. And now we compute this from this relation. We have this one, but a and g is equal to minus b and g prime t over 2 pi n. So we get this relation from this one, and this one, we get this relation. And here we have almost this relation. We must deal with the coefficient 1 over n square, but 1 over square is less or equal to 1, so we get this inequality, and we can see here that we have this relation. So we get this relation, and we have almost down. We simplify by t square by 1 over t, and we get what we want, and we get the Parseval identity. Now we will show under which conditions we have the equality, and I recall what we have seen, and we have this one equal to this one by using these two relations. This is equivalent to this equality, and now we can see that we can simplify by t square or by this coefficient, and we get this relation. For n equal to 1, the two quantities cancels, and we get this relation. But 1 minus 1 over n square is positive, this quantity is positive, so we get the sum of positive quantities. This means that all these quantities actually vanish, and we have this formula. So this a and g prime vanish, so A in G and B in G vanish. So this condition is equivalent to this one, and now we use Dirichlet's theorem. Dirichlet's theorem tells us that since G is continuous, the Fourier series converges to G, and we have shown this relation, so, and A0 is equal to 0, so we have what we need to do. And we have finished the proof of Wirtinger inequality. Now let's prove the isoperimetric inequality. So we are in this situation. Our purpose is to prove this relation. So we have a sample curve C. Here we have the area, we have a parametrization, and we have computed the area in function f. Now we make change of parametrization. We introduce this new parametrization of our curve in order to get thing easier. So from this relation we can see that x prime s is equal L over 2p u prime, and we factor by, if we take the square, we factor by L2 over 4p square. Now we consider this constant and we define this function, and we will see that this function satisfies the hypothesis of Wirtinger inequality. If you take its integral is equal to 0, it's a periodic function of period 2p, because we have made a change, and we can use Wirtinger inequality to have this relation, because this function is periodic of period 2 pi. Now we pursue, so we have we recall what we have done now, and now we have also this relation, because we have seen that this quantity is equal to L square over 4 pi square, and we get this relation. So we have now L square 2 equal to this quantity. We will also compute the area, this area. We make a change of variable L over 2 pi t here. ds is equal L over 2 pi dt. And now L over 2 pi v prime t is equal to y prime t. And if we add this constant, we get the integral of y prime t, but y prime is y is periodic. The integral of y prime is equal to 0, so we get the area. So now we have the area is equal to this quantity, and L2 square equal to entity. It's what we will use here. So now we will compute L2 square minus 4 pi I by using these two formulas. And if we do so, we get this relation, but this relation can also be written, we can write this as z prime s square minus zs square, and plus zs minus y square s square. If if you expand these two quantity, you get this one easily. And what is important here is that this integral is positive by Wirtinger inequality, and this one is positive because this function is a square and it is positive. So we have done. So we prove that L square minus 4 pi I is bigger than 0, and we get the isoperimetric identity. Now we will deal with the equality. We will see when we have the equality, namely that this quantity is equal to 0, and this quantity is equal to 0 since we have here the sum of two positive quantities. This means that this quantity is equal to 0 and this one equal to 0. And we know that for the integral of a positive continuous function vanish if and only if the function vanishes. So we get that this is equal to 0 if we have the equality in Wirtinger formula, but we have seen that we have the equality in Wirtinger formula if the function is a combination of cosine and sine, and here we get that y prime is equal to z, and so we get xs equal to this quantity and ys. And this is the parametrization of our curve, and if you compute this quantity you get a constant. So C is a circle of center x0 y0 and of radius the root square of a square b square. And we have done. So now we have completed the proof of the isoperimetric inequality. So to support the channel, please like, subscribe and share, and thank you.